Okay, um, so what about this first one here? True or false? Let's do a show of hands. True? False? Two falses? Three falses? It's false. Okay? It's false. Just because a sequence goes to zero does not mean that when you add up all the pieces it goes to zero. All right? An example is a harmonic. A harmonic sequence, a harmonic series, 1 over 2, 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Each one of those terms gets smaller, so the sequence goes to zero, but when you add them up, it diverges. It goes to infinity. So what about the other way around? If the sequence converges, if the series converges, if your series converges, does that mean that your sequence must converge? That way is true. So, okay. Now, how about number 2? Like I said, this was the first problem out of the homework set. So today was really just about, have you done your homework? Are you keeping up with your homework? Because we have a test a week from today, right? A week from today. It covers a lot of material. Last night and the night before, I started. I haven't done the homework for 7.3 is where I started. Isn't that the Shells method? I think it's 7. I did all the homework from 7.3 to 8.2 last night. So, of course, I know what I'm doing, and that's different. But still, if you have to stay on track here, okay? That's why you need to be staying up to pace. If I give you a quiz on the first problem of the homework assignment that I assigned 48 hours ago, you should know what this is. You should be able to answer this. So, yeah. How do we do it? So let me go to my homework assignments. I'll put all these solutions out later. Chapter 8 solutions. 8.2. Okay, so here's the solution. First of all, we recognize, hopefully, that it is geometric. Now, I used n's instead of k's because that's what the book uses. I want to make sure you understand that the book loves to use n, but I like to use k. And I told you last class why it is I use k and not n. Do you remember why? Well, the book uses this, sum n equals 1 to infinity, right? And I use sum k equals 1 to infinity. And the reason why is because when we talk about the nth partial sum, that means you sum and you stop at n, right? You don't go to infinity, you stop at n. So if I stop at n, I've got to use a different variable for my index, which is why I always use k. What the book does is when they want to do a partial sum, they keep the n here, but they start using i's instead. So this is like a dummy variable. You can use k, j, doesn't matter. N, I like to use k. All right, now I'm trying to get it to look like this. Sum k equals 1 to infinity, a r to the k minus 1, which is geometric, right? So what I need to do is try and get a number raised to k minus 1, and then that series will converge if what? This converges if what? If r, the absolute value of r is less than 1, and diverges if r is bigger than 1, right? So the first thing I did was I already have a negative 3 to the n minus 1, so I'm happy about that. All I need to do is make the 4 be an 4 to the n minus 1. So I make it 4 to the n minus 1 plus 1. Then I split that apart into 2 pieces. The 4 down here becomes a 1/4 out front. The negative 3 to the n minus 1 and the 4 to the n minus 1 become a negative 3/4 to the n minus 1. Right? Two things raised to the same power. You can create a fraction out of them. Y'all agree with that? And now I have an a and I have my r, right? So here's my sum. The absolute value of r is less is 3/4. That's less than 1, so it converges. What does it converge to? What's the formula? A over 1 minus r. A over 1 minus r. But r here is negative 3/4, so you have to do all this stuff, comes out to be 1/7. Okay? All right. What was the question you were asking about? Number 21, right? Oh, this is from 8.1? Yeah. I'll look at it. I mean, I'll talk about it. Because I already have it worked out, so it'll be easy. Number 21 right here. Garvik, I think we talked about this also, but I don't remember us having the factorial there. When you wrote the problem down, I don't remember you putting the factorial there. This problem had factorials in it, so it's a little different than the way we did it, okay? So what you're trying to do, this is 8.1, this is sequences, right? We're not adding things up, we're just trying to figure out where this sequence is going. So when you say 2n minus 1 factorial over 2n plus 1 factorial, I hope it's obvious that as n gets large, the numerator gets large and the denominator gets large. Like they both become infinitely big. Would you agree with that? It's like you have infinity over infinity, kind of. But you can't use L'Hopital's rule here. Why? Can't use L'Hopital's rule on any factorials because you can never take the derivative of a factorial. It doesn't make sense. So the only option I had here was to try and rewrite this. So remember what this means. Like 4 factorial means 4 times 3 times 2 times 1, right? So if I say 2n minus 1 factorial, that means 2n minus 1 times the one below it times the one below that, right? Keep subtracting 1 each time. So I just decided to leave that one alone. But on this one, I actually tried to write out the pieces. So this is 2n plus 1 times 1 less than that. So what's 1 less than this? 2n, right? Then 1 less than that would be 2n minus 1, and then it keeps going, right? So since it keeps going, I put the factorial back on the end of that, and it matches up with what's in the numerator. We kind of call this like peeling it off. Like we're peeling off the first two factors of this thing out front. And then the rest of it is just the rest of the factorial, and then the top is everything else. Same thing, they cancel, right? You see that? So these two cancel, so this sequence just becomes this. And now I can let n go to infinity because there's no more factorials. And if n goes to infinity, you have a fixed number over something getting infinitely large, and that's going to converge to 0. So that sequence converges to 0. Does that help?
Yeah, I was just got me stuck with the factorial.
Yeah.
But yeah, it makes sense.
This is something that comes up. Math people, people who are going to do a lot more, math. This whole like peeling off stuff, this happens a lot. It's going to happen a lot in the next section on Monday. On Monday, we're going to be doing a lot more of this. So are there any questions on what I did here? Yes?
An exam, would you just for sequence, or just improve that, like, have like a limit?
I'm sorry?
An exam, or just improve that limit, or conversion divergence? Like, we're not going to be proving that it's increasing, so I'm asking.
Not, well, I mean, the problem would be, does this converge or diverge? If it converges, what does it converge to? So your approach would be, well, do this, and then show that it converges to 0. I don't know if that answers your question or not. Okay. All right. Anything else over homework? I'll post these answers at some point, but I'll just kind of real quickly run through these. I mean, when I say quickly, I mean super quickly. Like I'm doing some L'Hopital rule in here on 11. Here another L'Hopital. Here was not L'Hopital. It was kind of like I had to mess around, come through and multiply top and bottom by something to make things look better. This one I used the absolute value to show that it converged. This one I used the fact that it oscillated. This one I had to play with the factorials. This one required L'Hopital's rule twice. This one was squeeze theorem. This one was crazy. 27 required some stuff from Cal 1. Uh, Trying to figure out what happens to something when it has the form, an indeterminate form of 1 to the infinity, and you have to take natural log on both sides and pull the power down. It's a mess. So you might have to go back and review the section on L'Hopital's rule in indeterminate forms. More L'Hopital in there, more L'Hopital. This one was just inspection. This one I had to use a property of logs, that 2 logs subtracted becomes 1 log with division. This one here was the one I did in class I got stuck on. Remember that one? That one was just like this. Actually, it might even be the same problem. Squeeze theorem. Okay. So I just want to show you that so you can see kind of like in 8.1 the type of things you're going to be seeing on a test. You're going to be having problems with L'Hopital in there and stuff like that, and it's all kind of mixed up. So be ready for that sort of thing. 8.2 I'm not even talking about. Well, 8.2 did the homework for there. That's the geometric one. This 11 was geometric again. This one was geometric again. This one was not geometric. This one was geometric. This one was not geometric, but something else. Harmonic. Collapsing, telescopic. Remember that last class? That's that one. Another collapsing telescopic one. So it's all fun and games. Yes. 15? Okay, 15. We're trying to figure out what's happening when you add up the terms of this sequence, right? Add them up forever. So the first thing I do is I take a look at the sequence, and I always want to ask myself, where does that sequence go? Because if the limit of that sequence goes to somewhere, if the limit of a sequence goes to somewhere other than 0, what can you tell me? Well, it's right here. If the sequence goes somewhere other than 0, automatically the series diverged. Because look, what's happening is each one of these terms in this sequence, as I go out bigger and bigger values of n, it gets closer and closer to 1/3. So it's basically like I'm stacking the 1/3 on top of 1/3 on top of 1/3 forever, and that's just going to get infinitely big. So I always look at a sequence and ask myself, what's the limit as n goes to infinity? If that goes somewhere other than 0, I'm done. It diverges. Is that what you were asking? Or? Yeah. So it's not harmonic. Okay, it's time for today's stuff.
So on the test, are you wanting us to classify the words that we use on each one?
Yeah, in your work, I'm going to need to see like you understand what you're doing. I mean, like I think I said last time, you can't just say like converges or diverges. And you have to have some sort of reasoning, rationale behind it. Yeah. Especially now that we're getting these next few sections, you'll see that we have to be very explicit in the way we do things to come up with a conclusion. All right. All right, this is something I didn't cover. It's out of 8.2. It's something I didn't say last class. It's just a theorem. It says that if you have 2 series that converge, all right, so you got one series has a certain sequence inside of it, another sequence here. If both of those converge, then if you multiply the sequence, or the series, sorry, by a constant, or if you add these 2 series together, that answer also converges. So that seems to kind of make sense. And if you add them together, it's the same as adding the terms together and then summing them or doing them separately. Now, the reason why this is so critical for me to point this out to you is that it does not tell, this theorem tells you nothing about if they diverge. Okay, it says if they converge, then you can add them together and get an answer. But if they diverge, you can't. So we did an example last class that was a telescopic Okay, it was telescopic, harmonic. And what we did was we took this here and we did partial fraction decomposition on it. Do you remember that? And so we took this and we did, let's get the A and the B, and we split it up into two pieces, didn't we? Well, 1 over n is harmonic. Why? It just keeps going up by 1 in the denominator, right? That's what harmonic is. And then this one is also harmonic, because every time the denominator keeps going up by 1. So you might be saying to yourself, oh, okay, look, this is harmonic, they both diverge, therefore the whole thing diverges, right? But that's not what that theorem says. The theorem says is if they both converge, then you add them, it will converge. If they both diverge, you don't know anything. You can't even say it diverges. In fact, we showed in class last time, this was telescopic and the ends stayed and the middle fell apart. Remember? Like the terms in the middle were canceling each other out, and we were left with a little bit in the front and a little bit of the back, and we took a limit and we got an answer. So it did converge. You understand what I'm saying here? It's real important that you kind of get that just because you see harmonics separated like this doesn't mean it diverges. Let's see if I put this here. See? But this is collapsing. This actually adds up to be 1. And you can actually see page 439, example 6. They actually worked that problem out in detail. So that's something I don't want to see, you do on a test where you take something, you do your partial fraction decomposition, you split it apart, and you say, oh, harmonic on each, diverges, done. That's not the case. With me? Okay, we're going to start 8.3. The notes. Oh, yeah, I'm going to put up I think the notes from last class are up. I don't recall if I put them up now, but they are or not? They are. The notes are up. The lecture's up. The answers to the problems aren't up yet. When I put this up today or tomorrow, I'll put everything out there. Okay, so we're in 8.3. 8.3, there's a lot of stuff in here, all right? We are now trying to basically figure out when a series converges and when it doesn't, all right? In the previous section, we looked at how many different series? 3? What were they? Harmonic, telescopic, geometric, right? And for each of those, we were able to determine an answer. Like geometric, if it converged, it was A over 1 minus R, right? If it diverged, it diverged. Harmonic always diverges. And then telescopic, well, we would have to do the computation, get everything in the middle to cancel, and then we get an answer, wouldn't we? In this section, we're not so much concerned with the answer. We're just concerned with does it converge or not. Like, does it converge or does it not converge? So the first thing we're going to talk about is the integral test. So I want us to look at this series here. The series we have is sum k equals 1 to infinity of 1 over k squared. And I wrote out the first 3 terms of this series. Is that geometric? What's the thing that keys you that it's geometric? That you have -1, and then the k is in the power, right? So k isn't even in the power, so it's not geometric. Is it harmonic? No, because the denominator is not going up by 1 each time. Or not 1, it could go up by like 2 or 3. This one, it's squaring each time. So it's not harmonic. Is it telescopic? Well, you would have to do like a partial fraction decomposition on it. So maybe, but I don't even think so. So here's what we're going to do. We are going to look at 2 things. We're going to look at, first of all, the sequence. Sequence means the list of numbers, right? The red dots are the the series added up. So this is the first sum. That's if I take the first guy right here, right? The first one, that's 1. If I take 1 plus, the next one is what, a fourth? That's 1/4. The next one is a ninth, that's 1/9. The next one is 1/16. So the red dots are the sequence. I just said series. They are the sequence of numbers, right? Y'all with me on that? Now the black is the curve that represents this as a function. So replacing the k with x and looking at it as a real valued function, that's a nice curve, isn't it? We okay with this? So when I add up, when I'm trying to add 1 plus 1/4 plus 1/9, couldn't I look at it as adding this, this rectangle right here, right? 1. Why does this rectangle have an area of 1? How high is it? It's 1. And how wide is it? 1. Okay, now if I want to add this rectangle, how high is it? Plug 2 in, you get 1/4. How wide is it? It goes from 1 to 2, right? So it's 1 wide. Each of these rectangles is 1 wide, right? So the area of each of those rectangles is actually the height of each of the rectangles. So isn't the area of the red rectangles together 1 plus 1/4 plus 1/9 plus 1/16 plus and forever? Isn't that what it is? Isn't that the geometric, or not geometric, isn't that the series I'm trying to add up right here? Yes? So adding all these red rectangles together, that sum is what I'm trying to find. Yes? But look at this. That sum of all those rectangles together is less than the integral of the black function from 1 to infinity plus 1. So where's 1? Right here? 1 goes up to here. So starting here and looking at the area from here on, do you agree that the area under the black curve is bigger than the sum of those rectangles? Right? Because there's like it's adding that much more each time. So that's from 1 to infinity, but then I have to say plus 1 to cover this rectangle also. So the sum of all the rectangles is less than that integral plus that 1 that takes care of that rectangle right there. Do y'all see it?
So it's only less because of the plus 1?
It's only less because of this. Like the area under the curve, right? If this integral right here represents everything under the curve, right? Everything, including that white area. So it's more than I'm actually looking for, isn't it? Okay. So y'all agree with that inequality over here? That's true? Everyone's clear on where the 1 came from? Okay, so now I'm going to work something out now. If this sum of the rectangles is less than that integral, then I can find the antiderivative of that, right? Like, what's the antiderivative of 1 over x squared? Negative x to the negative 1, which is this. And then you can plug in infinity. What happens if I plug in infinity? 1 over infinity goes to what? 0, so I get 0. What if I plug in 1? I get negative 1, so I subtract negative 1. And then plus 1, that comes from that one piece at the end. So isn't this integral plus 1 equal to 2? So what we're saying is that the sum of all my rectangles is less than or equal to 2? So what can I say then? It's got to converge then. It's got to converge. Because what's happening is that I'm adding, like every rectangle adds more area each time, right? But I'm saying that I can't go past 2. There's something bigger than it, 2. So it's converging to something, but I can't tell you what it is. See, careful. I don't know what it converges to. All I can say is that it's less than 2. But I can say it converges. Does that make sense? We're using the integral to actually give us like an upper bound on the sum, on the series.
So that's the answer?
The answer is it converges. So we're not looking in this section as much, at what does it converge to? It's does it converge or not. So what we did here is what we're going to call the integral test. We showed that our sum is bounded.
So that's like an approximation of what it is.
Well,
Like,
it's less than 2.
It is, but it's saying it's approximately close to somewhere around 2.
Well, I don't even know how close to 2 I am. I don't. It actually, the true answer is pi squared over 6. Yeah, and that's not, you know what I'm saying? Like, that's not, it's not close enough to 2. Um, it just gives us a bound. As soon as we have a bound, I can say I've got to converge. Is that all right? Okay, let's look at this one. So now I changed up the series. Instead of 1 over k squared, I put 1 over the square root of k. So the terms are 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4 forever. I set up the same thing. I've got rectangles in here, okay? If I look at these areas, just like I did before, I've got 1 over root 2, 1 over root 3. So I've got all these areas together. And then here, the black curve is 1 over the square root of x. Do you notice that these rectangles are bigger? Do y'all see how these rectangles are bigger? So the relationship that we have is a little different in this problem. The relationship we have is that if I add up all the rectangles, right, if I take that series, the series is actually bigger than that integral, isn't it? Because I've got that little excess space right there that's above this curve. So every time I add a rectangle, I'm adding a little more than what the area under the curve would be. So that's the relationship. This sum is bigger than or equal to this integral. And then when you compute this integral, which everyone here could do, right? When you get that integral and do all the work for it, I'm not going to do it, you get infinity. So what does that mean? Our sum, right, our series, has to be bigger than infinity. Well, you can't be bigger than infinity unless you're infinity also, right? So that means that this sum gets infinitely large also. So it diverges. Yes?
So if we're doing these problems on our own, how will we know that the rectangles are like bigger?
I was hoping someone would ask that question. The good news is you're not going to have to, because I'm going to give you the theorem, and the theorem tells you what you need in order to determine this. All right, but I wanted you to see where the integral test comes from, or the integral test. Where does it come from? It comes from this geometric idea. Now the theorem, hopefully that's what's next. Yes, is right here. Okay, that's the integral test, right there. And I'm trying to find a size here that fits on the screen. Is that big enough for y'all to read? Okay, the integral test. By the way, I handed you this sheet today, right? Everyone should have this. Look at the first thing on this row here. By the way, this is a very old sheet. I used to hand this out when I used to teach Cal 2 like 7-8 years ago. So the notation's a little different than what we do in this class, but it's close enough. The nth term test. This is a summary of all the tests that you have for series, all right? The nth term test. You have a series a sub n. It diverges if the limit doesn't go to 0. And then look at the comment on the side. It's inconclusive if the limit does go to 0. That was the first question on your quiz today. I said, if a sub n goes to 0, does that mean the series converges? And this says, look, if a sub n goes to 0, you don't know. All right, so then the next thing is geometric series, right? So that's what we've already done. Skip over P series. I'm about to do that, but I'm going to do integral first. So the integral test is what I'm doing right now, which is on the board. And the integral test says this. This is extremely important that you have to have these things happen first. First of all, I have to have a function that's positive, decreasing, and continuous. So remember I came in with that black curve, right? I had all my rectangles, I had that black curve. That curve has to be positive. What does that mean? Above the x-axis. It has to be decreasing, which means that it's always going down. How can you tell if a function is decreasing? Cal 1, Cal 1. How do you know if a function is decreasing versus increasing? Cal 1. What? How do you, what can you do if someone gives you a function, they want to know if it's going up or down, what do you look at? Mm, if what's negative or positive?
Function.
Well, that just tells me if it's above or below the x-axis, though. You're close. Negative or positive, but not the function. The derivative. Remember the derivative? If a derivative is positive, it means your slope of your tangent line's like this, right? Which means your function's going up. If your derivative is negative, that means you're going down, right? So for me to be able to determine it's decreasing, I'm going to actually have to look at the derivative of the function to confirm that it's decreasing. And then continuous, well, continuous just means it's defined on this interval, 1 to infinity. So let's say we have a function that's continuous, it's positive, and it's decreasing on the interval 1 to infinity. And then let a sub n be equal to f of n. That means all I'm going to do is plug in integers into my function, right? Instead of all the real numbers, just the integers. Then the series is convergent if, what does if mean? If and only if. That means this series is convergent if and only if the integral is convergent. If and only if is an extremely strong condition. It means that if this guy converges, this guy converges. And if this converges, this converges. And if this diverges, this diverges. And if this diverges, this diverges. I mean, whatever one does, the other one has to do also. The if and only if goes both directions. So it means that if the integral you do converges, automatically the series does. If the integral diverges, the series diverges. And you're done. So you don't have to draw pictures of rectangles or anything like that. All you have to do is make sure that it's a positive decreasing continuous function. That you have to do. Again, though, in the red here, I have an important note here. This test does not tell us exactly what the series converges to, only tells us if it converges or not. All right, so here's our example. That I'm not working these out. I have some that I am going to work out today, but these I'm not. When does this series converge? So it's the series sum k equals 1 to infinity of 1 over k to the p. This is known as a p series. Can you tell me when it converges according to what I handed you today? It converges if p is bigger than 1, and it diverges if p is less than or equal to 1. Okay? That's from the table. Now I actually go through the work of showing why. So the first thing I do, and it's important to go through this because this is what we're going to do in the next few examples. I look at 1 over k to the p, and I look at that right there as a function of x. 1 over x to the p, which is the same as x to the negative p. Now, let me ask you this. Is that a continuous function on 1 to infinity? Where's the only place this function is undefined? What's the only value I cannot plug in for x here? 0, right? I get division by 0. So that is definitely an okay function on the interval 1 to infinity. Because remember, all I have to do is integrate from 1 to infinity. So that's okay. I'm good there. I'm continuous. Also, the function is positive. Why? Why is this function positive?
Take the derivative.
Not derivative yet. I just want to know if this function is above the x-axis or not. Well, what if I plug in negative 2? What's 1 over negative 2? Well, it might be negative, right? Depending on the power. But what interval am I on?
Positive.
1 to infinity, right? So if I plug a positive number in here, it doesn't matter what power I raise it to. It's going to be positive still, right? So positive over positive is going to be positive. So this function lies above the x-axis no matter what, on the interval 1 to infinity. Now I have to take the derivative. The derivative of x to the negative p is negative p x to the negative p minus 1, which is actually negative p x to the negative quantity p plus 1. So I just factored a negative out here. And then if you have a negative exponent, you drop it to the bottom, and that's this. Now, what is the derivative, positive or negative? So you have to determine if it's decreasing or not. I say here, where is it? So the derivative is negative on 1 infinity. Why is the derivative negative? The numerator is negative, right? Negative p. And then what about down here? I'm plugging in what numbers? Positive numbers? So if I plug in positive numbers, negative over positive should be negative. So my derivative is negative, which means that my function is decreasing. So I've got a continuous function that's positive and decreasing. I checked all that. Now I can apply the integral test. Integral test says take the integral from 1 to infinity of this. There's your function. There's the antiderivative. Then you have to plug in infinity and 1 for x and figure out what it is. We did this before in a past class, so I'm not going to go through all the work again. But there's like these different cases. And when you look at these different cases for p, you actually figure out whether or not that integral converges or diverges. So the summary of it all, though, is what it says on that piece of paper. This integral will converge if p is greater than 1 and diverge if p is less than or equal to 1. And whatever the integral does, this series must do also. And that's it. Most important thing of me showing you this is for you to see how I was looking at the continuity, the positive, and then the decreasing, how I had to do that. If you don't check your function, then it's going to be counted off on the test. You've got to make sure those conditions are met before you can start applying the integral test. You ready to do this? We're ready to start some examples. I can't tell you how thrilled you all look right now. Okay, tell me about A. Converges, why? Or why not?
It's positive.
What's positive?
K squared. It's like a parabola.
Yes?
It's in the opposite. It's in the positive range of x.
But it stays within 1 to infinity, so it constantly stays positive.
So it should be a positive.
Is that a P series? I mean, look at what I just had up here. Boxed off here in black. A P series, that's what we're going to call them, P series, is any time you have sum k equals 1 to infinity at 1 over k to the p. K to the p. Do we have 1 over k to the p here for this first one?
You have like 1 over k to the negative 2.
Yes, you do. That's what I was hoping you would see. You have sum k equals 1 to infinity of what again? 1 over k to the negative 2. So all you did was drop that k squared down as negative 2, right? That's the same. Now, does that look like a P series? With P being what? This is a P series with P being equal to negative 2. According to my sheet here, this will what? Diverge. I don't have to do any work, okay? You don't have to do any work on P series. All right? You don't. But you have to identify them as P series. What about the next one? Is that P series? It's 1 over k to the what? 1/3. So that's P series, isn't it? P series. And P being what? 1/3, right? And that does what? Converges. What does it converge to? I don't know. And I frankly don't care because that's not what was asked. What was asked is does it converge or diverge? It converges. Question?
Isn't it smaller than one?
Oh, wait, hold on.
Yeah, that's what I was like, what?
Yeah, I don't know why I put that.
I still wrote divergence.
Got ahead of myself, I guess. 1/3's not bigger than 1? Not today. 1/3 is smaller than 1. It diverges still. Thanks for catching that. What about the next one?
Maybe P equals 1.5, right?
It's 1 over k to the what? What's the power on that? Can you put those together?
3/2.
3/2, right? 1 plus a half. That's P series with P, 3/2. This one converges, right? Because 3/2 is bigger than 1, right? But now I can say, what does it converge to? I don't know. Those are pretty straightforward, right? I mean, it's just a matter of identification, and that's it. Those series will pop up all throughout the next few sections. And it'll just be like, ah, boom, P series, boom, I know it does this, okay? But it's very different than this example. So let me give myself some room here. You want to do the whole next test, just a bunch of P series? We'll call it a semester. Let's do it. Does this converge or diverge? Okay, let's rule out some things first of all. What's the limit as k goes to infinity? So what I'm doing is I'm looking at the sequence inside, and I'm saying, where does that go? Let k get big. Where does it go? Infinity over infinity? Can you do L'Hopital on this? Yes, do it once. 2k over 3k squared? That's 2k over 3k squared. You can cancel a k. 2 over 3k. Where does that go? 0. The inside here goes to 0. What does that tell me? What I'm doing is what's called the nth term test right now. I'm looking at the inside and I'm saying, where does it go? It went into where? Where does it go? To 0, we said? What does that mean? Well, we don't know shit, is what it means, right? It's inconclusive. But you have to do that because what if it went to 1? Good, I'm done, right? It diverged. I'm done. And I'm not wasting my time doing a bunch of stuff I don't need to. So that's always should be the first thing you check. What is the limit of this inside piece? If it goes to 0, well, sorry, you got to try something else now. Okay? Is it geometric? K is not in the power, right? It's not geometric. Is it harmonic?
No.
Not even close, right? Is it P series? Well, kind of, but the problem is I've got that thing up there, right? I got a k squared up here.
But you can
Whenever
bring
you
it
do
down.
this, subtracting k squared to minus k.
Well, you can't do these two because there's 2 terms down here. You know what I'm saying? Like it's 1 term over 2. You can't split that into 2. You could do it the other way if it was.
Combine them once you bring it down.
You could bring it down and then multiply it through, but you're still going to have, you would have a k to the negative 2 here, and you'd have a k down here.
And then you can't.
Can't put those together.
Did you add 1 and minus 1 at the top?
Add 1 minus 1. Okay. Add 1 minus 1. But this is k squared, not k cubed. Right? I don't know if that's what you were going for to make it cancel or something. Okay, so we're kind of stuck, right? We're kind of at a point now. It's like, well, what do we do? Maybe the integral test will work. I mean, look at how many tests you have, right? We are going to get through every single one of these tests, except alternating series test, by the end of next class. So this is all going to be on the test next week. It's oof. Okay. So what do we need for the integral test? We need a function, right? I need to have function f of x. That's basically my sequence with all my k's replaced with x's, right? Let me take a look at that function. What I need to make sure is that that function, first of all, is continuous on 1 to infinity. Is it continuous? It's continuous on the interval 1 to infinity. Yes, it is, because, well, there's no values that are going to mess this up except what? -1? And that's not even a concern because I'm not even in that interval. So that's continuous function. Is it a positive function? Is it greater than 0? Well, the numerator is always greater than 0. The denominator is always greater than 0 as long as I'm plugging positive numbers in, right? So this function is always greater than 0 on the interval 1 to infinity. So I've got that. See, but I'm putting this down. I'm writing it down. And I'm making sure I'm checking these things. What? Yeah, it's like a checklist. What's the last thing on my checklist? Does it decrease? And how do you find if it decreases? Derivative. So what's the derivative of this function? That's L'Hopital's rule. Hold on. This quotient rule. Derivative of a quotient. Derivative of top times the bottom minus derivative of bottom times the top all over the bottom squared, right? High D low minus low D high, if you've learned it that way. Remember that? Cal 1? Derivative of the top, 2x times the bottom minus derivative of the bottom times the top all over the bottom squared, right? I need to verify that that's positive. So let me try by, do you want to multiply things out here? Let me just multiply that whole numerator out. It's 2x x to the fourth plus 2x minus 3x to the fourth. Is that right? All over x cubed plus 1 squared. I'm not even concerned about the denominator, right? I mean, my denominator is always going to be positive, isn't it? What about the numerator? Okay, so doesn't this turn into 2x minus x to the fourth? All over, I'm not even going to write it down. The bottom's positive, right? That's all I care about? What can you tell me about this numerator? You want to try and factor, or how do you want to do this? Pull an x out? Is this, what are we trying to make sure that this derivative is? That's always negative, right? Is it always negative though? I mean, try plugging in not 0, let's try plugging in 1 right now. What happens at 1? 1 times, let's see, isn't that a positive number over a positive, right? So it's not decreasing at 1, is it? What about at 2? Plug in 2, you get 2 times minus 6. So that would be negative, wouldn't it? In fact, if I go any number now, right? If I plug in 3, 2 minus 3 cubed is going to be negative. So what we need for this, let's see if I put it up here. I don't remember if I did. Where's my integral test? That's right. Where are we? Right here? Even though at 1 it was positive, right? After 1 it was negative the rest of the way, which means that even though my function might have come up a little bit, it's now going to start going down and continue going down forever. So that one little problem at just the single point 1 is not going to throw off the rest of it. So I'm going to say f is decreasing on, I'm going to say 1 infinity instead of closed interval 1. And that's good enough. So, what now?
Can you go by a few, like the first?
Yeah, it can be finite, but eventually has to go down. So what am I going to do now? Now that I've found a function that satisfies the criteria for integral test, I'm going to do what?
Antiderivative?
I'm going to find the integral, right? I'm going to compute this integral now. So I'm going to compute the integral 1 to infinity of, what was it, x squared over x cubed plus 1, and basic u substitution. I see something in its derivative, right? Almost. U is equal to x cubed plus 1. Du is 3x squared dx, which means 1/3 du is x squared dx. This integral now turns into 1/3, comes out, integral 1 over u du. And the antiderivative of 1 over u is natural log u. So you get 1/3 natural log u plus a constant, right? But I don't care about plus a constant because this is going to be a definite integral. I'm going to be plugging values in later. Let me replace u with what it is. What is u? X cubed plus 1. Everybody follow this? Now I'm ready to get to this. I want to take this integral here, and this becomes then 1/3 natural log x cubed plus 1 evaluated from 1 to infinity. What happens when you plug in infinity? Infinity cubed plus 1 is infinity. What's the natural log of infinity? Infinity. Done. This diverges. Right? So we're done. I could put here it's infinity, and then if you plug in 1, who cares? Minus some number, who cares? That means it's infinite. Therefore, here's my final conclusion. Therefore, sum k equals 1 to infinity k squared over k cubed plus 1 diverges. So it's a little involved, the integral test. You have to convert the sequence into a function. You have to verify that it's continuous, verify that it's positive, verify that the function is eventually decreasing, and then after you've verified all that, then you have to integrate it, plug in your limits of integration. Your limits of integration are going to be, it's an improper integral because one of your limits of integration is infinity. You do all that, and then if it converges, your series converges. If it diverges, your series diverged. This is kind of like a lot of what we've done this class all balled up into one, isn't it? All right, that's the integral test. The next one is what's called the comparison test. So let's say we have two series. Again, a sub n, b sub n. These are, adding up all these terms forever. And they're both positive. What do you think I mean by positive? Every term is positive. So we're not talking about like an alternating series that went negative then positive, negative, positive. We're only talking, you can only use comparison test if you have if you're looking at positive series. The next section will deal with alternating, okay? Not today though. So let's say we've got two positive series. And let's say that the first series, right? This first one, a sub n, that each of the a sub k's is smaller than or equal to each of the b sub k's. So the first term of the series is smaller than the first one on the other one. The second one smaller than the second one. Third smaller than third. And that's always true. Well, I put eventually, and I'll talk about that in a minute. Eventually, this inequality holds. Then, oh wait, and let's say that this B sub n, this series converges. Then what can we say about the other one? It has to converge also. Because if this guy's always smaller than this one, and you add up all these and it goes to a number, then these have to add up and they can't be any bigger than that, right? So it's got to converge also. That kind of makes sense? And then it's, if you flip it around and do it the other way, then it should work also. If your A's are always bigger than your B's, and your B's diverge, if this becomes infinite, and this guy's got to be bigger than it, then it's got to diverge also. Yeah? All right. I think I'm ready to do this one. This is also on here, right? The comparison test is on here?
Yes.
Okay. Okay, so let's look at this first example, then we're going to work through one. Does this series converge or diverge? All right, so I look at this. What would the first thing you do be on this? Okay, L'Hopital, because you're trying to see what the inside goes to, right? And you're hoping it goes to something other than 0. Because if it does, you're done. You can say diverge. You can move on to the next problem. But when you do this and you do L'Hopital's rule, you'll find very quickly that this thing does go to 0. Since it goes to 0, you don't know anything. Okay? So the next thing to do would be possibly to see, is it geometric? No, because k is not in the exponent. Is it harmonic? Not even close, right? Because your denominators are going up by powers like a 4, right? It's like k to 4. It's not just jumping up by 1 each time. Y'all okay with that? Integral test. Could we turn this into a function? Like x squared minus 1 over 3x to the 4th plus 1? Sure. Would that be a continuous function? Probably. Is it always positive? Is this always positive? Well, at 1 it's 0, right? At 1 it's 0. But after you go past 1, that's positive, isn't it? Could you take the derivative? Sure. Do you want to? Maybe. I don't know. So integral test might actually work for this problem. It might. It might. But there's a much cleaner way to do it. And it's by using this comparison test. So what I'm going to do is this. I'm going to write out, first of all, the sequence. There's the sequence. And I put here it has positive terms as long as k is bigger than 1. So even though when I plug in 1 I get 0, once I get past 1, they're all positive, aren't they? What I want to find is some sequence, some other sequence, b sub k, where either my sequence is smaller than that sequence all the time, and that other sequence converges, or the other way around. My sequence is always bigger than that other sequence, and that sequence diverges. So, do y'all understand what I'm saying by this? What this means? This series right here, if I can show this sequence is smaller than something that goes to a number, I've got to go to a number. But if this is always bigger than another one, and that one goes to infinity, then I've got to go to infinity also, right? It's the hardest thing in these problems is coming up with that other sequence, because you got to go reach into the magic bag and pull it out. So here's the sequence, and here's the magic bag. Here's what I pulled out of the magic bag, right there. That's my b sub k. So I'm trying this. Do you agree that this is bigger than this?
You took out the plus 1.
What did I do? I didn't change the numerator, right? Numerators are the same. I made the denominator smaller. If your denominator gets smaller, the fraction gets bigger, right? So I took that 1 away, and that's, so do you agree now that this is bigger than this? You sure? No questions? Yes, no? Julia? Wait, you got that look? What's up?
No, I'm just trying to take it in.
So that doesn't make sense then? It's okay.
Yeah.
If anytime you have a fraction and you want to make it bigger, you can make the denominator smaller, or you can make the numerator bigger, right? I'll take 4/5, right? To make something bigger than that, I could go 4/4, couldn't I? I make the denominator of that smaller and the fraction gets bigger. I could have also have done 5/5, right? I could make the numerator bigger, leave the denominator alone. So when I'm doing that problem, where is it? Right here. What I did was I said, look, I would like to find something bigger than this. So what I could do is make the numerator smaller. Make the numerator bigger, right? Or I could make the denominator smaller. I chose to make the denominator smaller. How could I make the denominator smaller? Just take one away. Now it's a smaller number. Smaller number on the bottom makes it a bigger ratio. Is that okay? Now, the beauty of that is that now that I've taken the 1 out of this one, I can split this into 2 different pieces, can't I? I can do the k squared over this and the -1 over this. So I split them into 2. And now I reduce some powers, and I get 1/3k squared, and I get -1/3k to the 4th. Y'all okay with that? So what I have now is I've got this guy here, this sequence, is bounded by this one. Right? That's smaller than that all the time. So if I add these up, right, if I add all these guys up, it should be smaller than adding all these guys up, shouldn't it? Take those right here, add those all up, that's smaller than adding all these up. Y'all still there? Did I lose you at integration by parts like a few months ago? Y'all okay? Yes or no? I mean, you following this or not? Look at these right here individually. This guy right here is a p series, isn't it? I don't care about the 1/3 because constants don't matter. I could pull the constant out of the sum. It makes no difference. But that's a p series, 1/k to the p, with p being 2, right? That converges. This one by itself is also a p series with p being 4. That converges also. If 2 pieces converge, then when you subtract them, they converge also. That's the first thing I put on the board today after the quiz, didn't I? Right here. If these two converge, then when you add them up, they converge also. But I said, wait, if they diverge, you can't say that, right? Okay, but these, luckily for us, converged. So since these both converge, this whole thing converges, which means it goes to a number, doesn't it? And that means that the left side is smaller than or equal to a constant, which means that it converges. And I'm done. What do y'all feel like right now? I mean,
Do you have to put that? It's less than a constant?
well, if you had done this and, kind of said it
Right,
converges,
right, can we show that they both converge?
well, as long as you identify it's a p series, yeah,
So if that converges and it's bigger, which means the other one's smaller, so it's also.
that's right.
Because if that one converges, then the other one converges with it.
Yeah. Well, it's not that they go together. It's the fact that this one is just a bunch of things being added up, right? So let's say I keep on adding stuff up, and it keeps piling up, but what I can tell you is that this pile is always smaller than this pile, right? And that pile piles up to be here. Then all I can tell you, that what I can guarantee you is that my pile over here, as I add it up, if it's got to always stay under that, it's got to converge. It's got to eventually stop somewhere. Now it may converge here and not up here, but it's got to converge somewhere. I don't know where, but it converges. Okay. We're going to do an example now where I'm going to work through it. We're going to do two examples. I'm trying to get a sense for the way y'all feel. I don't know. I said I haven't taught how-to in a long time, but even when I used to teach it, I always do series, so I've never skipped over series. Um, but it just seems like it's been a long time since anyone's been exposed to it. Yes.
How come when you do Laplace rule, you get it that goes to zero? How is that different?
How is what?
The Laplace, the
Yeah.
order Laplace.
Yeah, that's all right.
How come that one goes to zero?
What do you mean?
We have to find all this stuff for it to converge.
Because just because each individual piece is getting smaller doesn't mean that when you throw them all into a pot, it's going to stay fixed. Is that, I don't know if that, like when we said in the very beginning of that problem that you look at the inside and the inside's going to zero, right? Just because that's happening doesn't tell you anything, though. We did this example earlier. It was 1/2 plus 1/4 plus 1/8 plus 1/16. This is a geometric series. That's the series basically. It's 1/2 to the k. This would converge, which means that if I keep adding these up, there's a number it won't go past. But if I look at 1/2 plus 1/3 plus 1/4 plus 1/5, this is harmonic, which means if I keep adding these up, it just keeps getting bigger and bigger. But if you look at these and do L'Hopital on this, or you don't even need L'Hopital, what happens? Each of these guys is getting smaller, right? So they're going towards zero. But when you add them up, it goes to infinity. Each of these is getting smaller. They're going to zero. But when you add them up, you get a number. So just because the pieces individually go to zero doesn't mean you can tell me if it converges or not. Does that make sense? I mean, all you can tell me is that if they don't converge, like if it's 1/2 plus 1/2 plus 1/2 plus 1/2 forever, that's going to just overfill.
The top one is going to converge because it goes fast.
It goes to zero faster than this one goes to zero. Yeah. It's all about how quickly you go. Okay. Does this converge? Ooh, wow. So you would maybe start with the nth term test. You try and say what happens on top and bottom as k goes to infinity.
So we gotta make like either the numerator or denominator smaller or bigger.
How do you mean? Oh no, you're already jumping right to comparison test, right?
But you want us to go through each one.
You have to look at the way you're going to approach these problems on a test. Okay? The approach would be, let me see if the inside pieces, let's see if each of these guys goes to zero or not. If they don't go to zero, I'm done, right?
Yeah. But since that k's in the power.
Yeah, how are you going to do this? I mean, the numerator goes to infinity over infinity, right? Let me write this down.
Wait, isn't that a AR
Geometric.
geometric?
It's looking geometric, right?
That's what I was.
It's looking geometric, but that 4 in front is a problem. That 4 plus is a problem.
Oh, if it was 4 times, it would be geometric.
Yeah, if it was 4 times, it would be. Okay, let me just see here real quick, though. What happens to this if you let k to go to infinity? Don't you get infinity over infinity? And then you'd have to do L'Hopital, right? You could also do this, though. Break them up. I like that. Good. And watch what I do here. So you can do the 4 over 2 to the k, which is here, plus then you can do the 3 to the k over 2 to the k, which is the same as 3 over 2 to the k, isn't it? Now let k go to infinity. What's 2 to the infinity?
0.
Well, then, yeah, 4 over that's going to go to 0. So this is headed towards 0 plus, what's 3 halves to the infinity? Infinity,
It's greater than 1.
right? Do y'all agree with that? Did I write this one down? This shouldn't be that easy. Yeah, that's it basically. I mean, we're done. Because this goes to 0, right? And we're adding to it 3 halves to the k. 3 halves is a number bigger than 1. As you start raising those to larger and larger powers, that becomes infinite. That means each of these terms gets bigger and bigger and bigger as we go out. So when we start adding them up, they're going to become infinitely large. So we're done. So the limit as n, or it's not n, the limit as k goes to infinity of 4 plus 3 to the k over 2 to the k goes to infinity, which means that this diverges. So we're done, right? We're done. But I would like for us to show it by comparison also, just so you can see it, all right? So I'm going to do the comparison on this one. I'll just do a little squiggly line here. What I need for comparison to work is I need to take the sequence 4 plus 3 to the k over 2 to the k, and I need to somehow try and figure out something that's bigger than it or smaller than it, right?
Just take away the 4.
Yeah, absolutely. That's what I would do. Good call. Take this sequence, take the 4 away. If you take the 4 away, then it'll look like this. 3 to the k over 2 to the k, right? Now, which one's bigger? The one on the left or the right?
The one on that.
The one on the left. So I could say this, right? That's true. But this one on the right is the same as 3 over 2 to the k, isn't it? But that's geometric with r being what? Basically, if I start adding these up, it's geometric with r being bigger than 1?
Yeah.
I mean, it's not k minus 1 yet, but you could make that a k minus 1, right? K minus 1 plus 1? And that would be geometric with r being what? 3 halves? Do you see what I'm saying there? I'll even write it down. This is the same as 3 over 2 k minus 1 times 3 over 2. That's this, but peeling off a 3 halves. So A is 3 halves, R is also 3 halves. Since this is geometric, with the absolute value of R being equal to 3 halves, which is bigger than 1, it diverges. And if this side over here diverges, when I add them all up, right, and this guy's bigger than it, it's got to also diverge. All right, let's look at another one.
What did you do with absolute value?
That's for geometric, you look at R and you take its absolute value and make sure it's less than 1 or greater than 1. It's always absolute value for that. Okay, does sum k equals 1 to infinity of 1 over square root k cubed plus 1 converge or not? Nth term test first. Nth term test. Take the inside, let k go to infinity. Where's it headed?
0.
0. 1 over infinity, right? 0. What does that tell us? Nothing. Nothing. Well, the sequence converges to 0, but that doesn't tell us anything about the sum, right? The series. So I have to do something else. Is it geometric?
Could you add the powers?
How do you mean?
Like 1/2 plus 3 like we did earlier?
Well, we have a 1 there, so you can't. I think you mean like this square root is like a 1/2.
Right.
Because of the 1, you can't split it into 2 because it's added. So you can't do anything with the root yet, but we will. Not geometric, not harmonic. Could you do integral test? Maybe, right? Maybe because you could do like a, look at that as a function. Is it always, is it continuous? Like if you look at the inside here as a function, is it continuous?
Yes.
Okay, is it positive all the time?
Yes.
Is it decreasing? I would need a derivative. I'm going to try and avoid that. So what I'm going to do is I'm going to write down a sub k equals this. And I'm going to try and find something that's either bigger than it or smaller than it over here. But whatever it is that I find over here, the b sub k that I'm looking for, needs to be something I know what it does. Like I know it converges or diverges. So take the 1 out. Let's see what happens. If you take the 1 out, you get this. Which one's bigger?
The one on the right.
The one on the right's bigger, right? Because you've made the denominator smaller, it makes the fraction bigger. But the right-hand side is really just 1 over k to what power?
1/3. I mean
3
3
halves, right? 1 over 3 halves? What kind of, if I make a series now, right? If I start adding these up, sum on both sides here, right? Sum here. If I start adding these up, what kind of series is this here?
P series.
P series, with P being,
Bigger than greater than 1.
what happens with the P series when P?
Is greater when diverges. Converges.
So look off your thing here, P series. If P is greater than 1, which it is, it converges. So this would converge, which means it's headed towards a number, right? And we must be what than that? Our series must be smaller than that, which means our series must also converge. Okay? So this sum k equals 1 to infinity of 1 over square root k cubed plus 1 is smaller than or equal to some number that I don't even know, which means that we converge. Questions? I had a problem I wanted to do earlier, but I forgot to write it down. Let me see if I can remember what it was. Sum k equals 1 to infinity of 1 over k times k plus 1.
Oh, we did this one already, right?
We've done something similar to this. This was telescopic. All right, so this is what we did last class. Let's try it with the comparison real quick. Let me just try this. If I pull down, this is my a sub k right here. And I try and find something that's bigger or smaller than this. How about I take away the k plus 1? If I take away k plus 1, is it going to get bigger or smaller?
So it could be smaller.
How are these two related? Which one of these is bigger? Remember, where does k start?
1.
1, right? So this would first be a what? A 2, and then it would be a 3, and then a 4, and then a 5. So which one of these is bigger? The one on the right's bigger, right? Do you all understand that? That's bigger, right? Yes? Okay, what kind of series is this? Harmonic, right? That's harmonic. What does harmonic do? Diverges. What does that tell me?
Your series. It doesn't tell you anything, right?
It doesn't tell you anything.
That's sweet.
Okay, that's what I wanted you to see by this. Because what we're saying is that if you take your series right here, right, that it's less than or equal to the sum of this series, which is infinite, right? So all you're telling me is that my series here is less than infinity. Less than infinity, not bigger than infinity. If it was bigger than infinity, then I would actually have to be bigger than infinity, so I have to be infinity also, right? But to be less than infinity means I can be 1, or I can be 2, or I can be 10, or I can be infinity or anything less than it, right? So this does not give me a constraint, a bound. So this is completely inconclusive and useless to me. And the only way to get this one would be with the telescopic. So just be careful with that. Don't get all gung-ho with this and think whatever this side does, this side does. You have to understand the inequality here. Okay, we are on the last topic of the day. It's called the limit comparison test. The limit comparison test says this. Let's say you have two positive series again. So just like the previous comparison test, we need to start with two positive series. And let's say you take the limit of each series stacked on top of one another like a fraction. So you put one series on top of the other, the sequence on top of the other. And let's say you take that limit and your limit comes out to be a number other than 0. Okay, other than 0. Then the series both converge or both diverge. So whatever one does, the other one does. So I have an example worked out here for you, and then I'll do one. And then we'll call it a day. And you've got a lot of work ahead of you for the weekend. Okay. Does this series converge? All right. Limit real quick. K goes to infinity. 1 over infinity, that's 0. That tells me nothing. Okay. Geometric, no. Harmonic, almost. If the 3 wasn't here, it'd be harmonic. But it's there, so too bad. Could I do that as a function and do integral test? Maybe. Could I do comparison test? Probably. But I want to demonstrate the limit comparison test. So that's the way I'm going to do it. You can take away the 3. In that way, if you took away the 3, it would be bigger than, right? And then that's harmonic. So you have infinity is bigger than. No, that wouldn't tell you anything. Yeah, you wouldn't be able to on that. Okay, so here we go. I've got to pick another. Sequence that I know what it does. So I come in here and I pick kind of randomly 1 over k. Now I'm kind of getting the 1 over k from the idea that this is kind of like 1 over k, right? I mean 1 over 2k plus 3 is pretty close to being 1 over k. It's 1 over a linear expression. So I'm just pulling this out of the air. And when I pull that out of the air, I say to myself, look, I know what that does, right? That diverges. It's harmonic. But now I'm going to take the limit of these two sequences stacked on top of one another. So a sub k was the original sequence of this series. That's 1 over 2k plus 3. B sub k was 1 over k. Flip that fraction around, right? 1 over k comes up. The k basically sits on top. And now take the limit of this. That's L'Hopital's rule, isn't it? Infinity over infinity. That gives you 1/2. 1/2 is a constant, right? 1/2 is not 0. The theorem up here said that if you take that limit and it turns out to be a constant, and that constant is not 0, then what? The series either both converge or both diverge.
So if it's not 0, then it diverges?
No, if it's not 0, then they both do the same thing. So it's not 0, right? So they both do the same thing. Well, the only one you know about is this one, right? What do you know about this one? It diverged. So the other one has to diverge also. Okay? So this is a cool test because you try and pick another sequence to put underneath it that you know something about. like you pick a p series or you pick a harmonic, and then you look at that ratio, and if that ratio limit comes out to be a number other than 0, then whatever the one you pick does, the other one has to do it also. I picked a harmonic. When I did the limit, it came out to 1/2, so they both have to behave like the harmonic one. They both have to diverge. Okay, let's look at this one. Find the sum k equals 1 to infinity of k plus 5 over cube root of k to the 7th plus k squared. We could check for ourselves that if you did do the limit, I'm not going to do it here, but that would go to 0, so that we don't know anything from that. It's not geometric. It's not harmonic. I don't even want to touch integral test on this because I can't even imagine integrating this, right? Because I'd have to integrate it at some point. I don't even want to touch that. Comparison test, maybe, but let's see the power of this limit comparison test. First of all, I have to write down my a sub k. And now I need to pick a b sub k. I'm going to choose, see the things I don't like are like, I don't like that plus 5, right? That plus 5, just, I wish it wasn't there. And then this right here, like the plus k squared, because if the 5 wasn't there and the k squared wasn't there, wouldn't this just be k to a power over k to a power? In fact, what would it be? If I get rid of the 5, I'm gonna go for this as my b selection here. I'd have k over the cube root of k to the 7th, right? Wouldn't I? Now let's figure out what that is. That's k over k to the 7/3, which is 1 over k to the 4/3. Do you agree? Or not? Now I need to make the ratio. What I'm going to be doing is I'm going to be taking the limit as k goes to infinity of k plus 5 over cube root k to the 7th plus k squared over 1 over k to the 4/3. You know what? I don't know why. I'm getting this feeling like I want to switch it back. Like I don't want to use this. I want to use this. Like I don't want to simplify it. Okay? I'm going to switch it back. You'll see why I think this is going to work better for us. I'll put it down here like this. Sorry I switched colors on you here. I'll put it in green. No, you can keep all that stuff out here. Is that what you're saying? Like this? I mean, that's all true, but that was just for fun, I guess. Let's see what happens here. Limit k goes to infinity. Now, the fractions kind of flip around, right? Like the bottom here comes up to the top, and this k goes to the bottom. So it'll be k plus 5 over cube root k to the 7th plus k squared times cube root of k to the 7th over k. Okay? 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 Now, the reason why I did this, because what I'm going to do is I'm going to take k to the 5th, k plus 5 over k. I'm going to put those together. Times, now these are both under the cube root, right? These are both cube roots. So couldn't I do this? Cube root of k to the 7th over k to the 7th plus k squared? Any questions on that? Since these are both under cube roots, I just make a fraction under a cube root. Let's let k go to infinity. What happens right here? Infinity over infinity. Couldn't you do a little L'Hopital on that? What would you get? 1 over 1 times. Now over here, inside this cube root, you would have infinity over infinity, wouldn't you? You could do L'Hopital. What would you do? What would you get if you did L'Hopital? 7k to the 6th over, I'll just do it, 7k to the 6th over 7k to the 6th plus 2k. That's infinity over infinity. So you go again. You would get 42k to the 5th over 42k to the 5th plus 2. So infinity over infinity. You go one more time, and it would basically turn into 1. I'm not going to do it. You have to do like 2 or 3 applications of L'Hopital's rule there. But to get rid of the 2 on the next one. So, but it goes to 1. And then under the cube root of 1 is 1. So what does that tell us? This ratio goes to 1. And if the ratio goes to somewhere other than 1, then they converge or diverge together. Well, hey, now we found some use for this. Here was what we came in with, right? That's what we came in with? What kind of sequence does that create? What kind of series does that create? P series, isn't it? With P being 4/3. What do P series 4/3 go to? They converge, which means they both must converge. Okay? We're done. Right? That ratio went to C equals 1. So whatever one of the series does, the other one has to. So this series, what was it, 1 over k to the 4/3? We know that that's a P series with P being 4/3 that converged.
So can we just stop right there?
Well, yes, but then you'd want to put something like, therefore, wow, that sum got crazy. Summation, I don't even remember what it was. K squared plus 5 over cube root k to the 7th plus k squared, wasn't that it? That converges. Now, it's time. I'll put all this stuff up on the web by tomorrow. I went through each of the problems for your homework out of this section. Your homework is going to be numbers 7, this is page 453, 7 through 29, odd. I went through these, and I determined for each problem which method to use. Like on number 12, it was P series. On number 24, it was comparison test. You know what I'm saying? Do you want that information, or you want to figure this out on your own? Maybe I'll wait. Because, I mean, to me, it makes no difference. Like, to me, when you're given a problem on a test, I'm not going to tell you, this is an integral test problem. You're going to have to figure that out. That's one of the hardest parts of this series, is you figuring out what test to use and how it works out. So, but if you're interested in that information, just contact me. I'll be happy to share that with you. All right? At least give you the hint. Oh, that's an integral test problem. Okay? Everyone have a good weekend. Do your homework. Come back ready. We have one more day of hell, then we have a test.
The grades for the test.
Oh, I have all your tests, your old stuff if you want it.